Section 1.6 is titled Acceleration Near the Earth's Surface, and it's a continuation on the discussion of motion in a straight line, uniformly accelerating motion. We could also call this free fall kinematics. In the absence of air resistance, all objects near the surface of the Earth accelerate towards the center of the Earth at a constant rate. So I want you to imagine you have a cell phone and it's in your hand at some height above the ground, and it accidentally falls out of your hand and starts falling towards the earth. So you know that its initial velocity when it leaves your hand is 0. And we want to describe its motion as it moves towards the ground. If it's starting off with an initial velocity of 0, we know that it'll speed up on its way to the ground. But what's causing it to speed up? And the answer to that is gravity. In fact, gravity causes all objects near the surface of the Earth to accelerate downward at a rate of 9.8 meters per second squared. And this is true on average on all locations around the Earth. So any object that is in free fall will experience an acceleration towards the Earth at this average rate of 9.8 meters per second squared down. And we give the symbol for this acceleration a little g in honor of the term gravity. So we say g is equal to 9.8 meters per second squared down. Now, physicists have determined that the average value of g is measured very close to the Earth's surface, and it's 9.8 meters per second squared down. But different places on Earth have different values for g. So for example, values of g in Mexico City are slightly but measurably lower than the average of 9.8 meters per second squared down. And this has to do with the fact that the city has a high elevation and is therefore farther from the center of the Earth. So there are two reasons or factors that affect the value of g. And the first, like in the case of Mexico City, is altitude. And the second is latitude. Now we'll describe both of these factors in more detail in Chapter 2. But for all of our calculations dealing with free fall kinematics, we will choose a value of 9.8 to represent the acceleration due to gravity. Now, the magnitude of gravity on Earth is different from the magnitude of gravity on different planets. We know that larger planets have larger values or forces of gravity, and smaller planets or celestial objects have smaller forces of gravity, and therefore the acceleration due to gravity on these different planets and different celestial objects will be different than that on Earth. In general, we can say bigger planets or celestial objects have bigger values of g and therefore accelerate at greater rates, whereas smaller planets or celestial objects have smaller values of g and therefore accelerate at smaller rates. For example, the Moon is a much smaller celestial object than planet Earth, and therefore objects near the surface of the Moon accelerate down towards the surface of the Moon at values much smaller than that on planet Earth. In fact, approximately 10 times smaller. When we first described freefall kinematics up above, we said that freefall kinematics occurred when objects fell towards the Earth in the absence of air resistance. Now we know that on planet Earth this is not true. Because the Earth has an atmosphere, that objects must experience resistance due to air, and this will affect the rates at which they accelerate towards the center of the Earth. But for all intents and purposes, when doing freefall kinematics equations, we assume that there is no air resistance at all. In fact, we assume that the objects are traveling in what we call a vacuum. So what would happen if there was air resistance? Well, in this case, objects would reach a terminal velocity. This is the velocity of an object when the force due to air resistance equals the force due to gravity on the objects. So they speed up as they move towards the center of the Earth, but eventually reach this terminal velocity, at which point they stop accelerating. And this occurs only in the presence of air resistance. To make our calculations simpler, we ignore air resistance and study free fall kinematics in the absence of air resistance. So let's take a look at sample problem number 1. Sample problem number 1 reads, a flower pot is knocked off a window ledge and accelerates uniformly to the ground. If the window ledge is 10.0 meters above the ground and there is no air resistance, how long does it take the flower pot to reach the ground? So, as we can see in this diagram, when the flower pot is traveling towards the ground, it will achieve a displacement of 10.0 meters down. It'll fall from the window ledge to the ground. Now, given that it's knocked off the ledge, we can assume that its initial velocity downward will be 0. So whenever an object is dropped from rest or is free falling from rest, its initial velocity is 0. And the moment we know an object is in free fall, we can write down that its acceleration will be due to gravity. And we give the symbol little g for gravity, and its magnitude is 9.8 meters per second squared down. This can also be called the object's acceleration, and we can use the symbol a for acceleration, just as we did in kinematics. If we do so, then we will be comfortable with using all of the kinematics equations that we have derived in section 1.5. The problem asks us to determine how long it takes for the flower pot to reach the ground. So essentially what we're looking for is to solve for delta t, the elapsed time. So if we take a look at what is given and what is required, we have delta d, v1, acceleration, and we want time. Looking through all of the equations that we have derived in kinematics, we can see that equation number 3 incorporates everything that is given and everything that is required. So that'll be our equation to use for this example. Equation 3 reads, delta d is equal to v1 delta t plus 1/2 a delta t squared. When using this equation, number 3, to solve for delta t, it poses a bit of a challenge. And the reason why is because delta t appears twice in this equation. First we have delta t and then we have delta t squared. So this is what we call a quadratic equation in mathematics. In order to solve a quadratic equation, we would have to use the quadratic formula. But we want to see if there is a trick in this question that will allow us to avoid the quadratic formula. And the trick lies in what is given. The initial criteria tells us that v1, the initial velocity, when this flower pot is knocked off the edge, is 0. If v1 is 0, then the first term in this equation, v1 delta t, can be canceled out because 0 times delta t is 0. The equation will then simplify to delta d is equal to 1/2 a delta t squared. So we have to isolate delta t in this newly simplified equation. And we've experienced this same situation in sample problem number 4 from section 1.5. When we rearrange this equation for delta t, we end up with delta t squared is equal to 2 times delta d divided by acceleration. But we're not quite done. We need to find delta t. So in order to find delta t, we have to take the square root of both sides. This will get rid of the little superscript 2. In this case, we end up with delta t is equal to the square root of 2 delta d divided by a. Now we are ready to sub and solve. So we have 2 times 10.0 meters down divided by 9.8 meters per second squared down. Square root of all of this. Remember that we're dealing with vectors here, so we have to take note of the direction. In this case, it doesn't pose a problem as both vectors are down. So we're able to proceed algebraically, punching it into our calculator and reporting it to the appropriate number of significant digits. Now, what do we choose for our number of significant digits? Well, 9.8 has two significant digits. And remember that 9.8 is a measured quantity, so it will affect the accuracy of our answer. So if we punch this into our calculator to two significant digits, we end up with an elapsed time of 1.4 seconds. So we can say that the time it takes for the flower pot to reach the ground from the windowsill is 1.4 seconds. Sample problem number 2 is a continuation from sample problem number 1, and it reads, what is the final velocity of the flower pot in sample problem number 1 just before it hits the ground? So if we recall, from the previous example, we know that the initial velocity of this object is 0, that it falls to the ground experiencing a displacement of 10.0 meters down, and since it's in free fall, its acceleration is equivalent to the acceleration due to gravity, which is 9.8 meters per second squared down, and we just calculated that the elapsed time for this fall is 1.4 seconds. What this question is asking us is, what is the final velocity? So what is v2? If we look at all of the quantities that are given and required, there are many options to the equations that we could use to solve this. I'm going to choose equation number 2, which states that final velocity is equal to initial velocity plus a delta t, or acceleration times time. Notice that we're not using the value for displacement, but we don't need to. We can use this equation because it incorporates everything we need and everything we have. So let's sub and solve. We end up with 0 plus 9.8 meters per second squared down times an elapsed time of 1.4 seconds. So punch this into your calculator and report your answer to two significant digits. If you do so, you should get that the final velocity of the flower pot is 14 meters per second down. On to sample problem number 3. A tennis ball is thrown straight up in the air, leaving the person's hand with an initial velocity of 3 meters per second. How high from where it was thrown does the ball go? We know that if we throw an object up in the air, it will eventually slow down when it reaches its maximum height. We now know that it is slowing down because of gravity. Gravity is causing the object to accelerate downward. So this object's speed will decrease until it reaches a maximum height. At maximum height, it's important to know that the object's velocity at that particular instant is 0. So this is one of the tricks of free fall kinematics that you need to remember. At maximum height, an object's velocity in free fall is 0. So the question asks us, how high from where it was thrown does the ball go? So we need to determine this maximum height that the ball travels. We'll call this delta d, its displacement upwards. And since this object is in free fall, we know right away and can write down that acceleration will be 9.8 meters per second squared down. The moment you hear free fall, you write down 9.8 meters per second squared down. We know that the object leaves this person's hand with an initial velocity, v1, of 3 meters per second in the upward direction. And we know that at the peak of its height, or at maximum height, that its final velocity will be 0. So remember this, when you see a max height question, you know that v2 will be 0 because the object has reached its maximum height. Looking at the variables that are given and the variable that is required, we can see that we need an equation that doesn't have delta t because we have no indication of the elapsed time. So that leads us to equation number 4 from kinematics. And this equation states that v2 squared is equal to v1 squared plus 2a delta d. We can rearrange this equation for delta d, and we've done this before in previous examples. Rearranging equation 4, we get delta d is equal to v2 squared minus v1 squared all over 2a. And now we're ready to sub and solve. So if we sub our quantities in, we get 0 minus 3.0 meters per second up squared divided by 2 times 9.8 meters per second squared down. Now an alarm should go off in your head, and since we're dealing with vectors, we have to note that these vectors, though they are collinear, they're not in the same direction. Our velocity is expressed in the direction up, whereas our acceleration is expressed down. So when we're calculating these algebraically, we're going to have to make sure that they're both in the same direction. If we flip the sign of one of these, then we will flip the direction. So let's choose up as our direction. When we change this, we will get negative bracket 3.0 meters per second up squared. And take special note that the negative sign is in front of the brackets. So when we square the velocity, that negative sign will remain outside of the bracket. Now we're going to divide this by negative 9.8 meters per second squared down. And I've drawn this in red pen to show that I've made this change. I've changed the directions so that they are both the same so that we can proceed algebraically. Now you can proceed, punch these into your calculator, report your displacement to 2 significant digits. If you do so, you will end up with a displacement of 0.46 meters up. This is our maximum height. In sample problem number 4, we want to determine how long it will take the ball shown above to reach its maximum height. So we have to start by writing down everything we know. We know that the initial velocity of the ball is 3.0 meters per second up. We know that when it reaches its maximum height, the ball has a velocity of 0. We know that since it's in free fall, its acceleration is 9.8 meters per second squared down, and we want to find the time it takes or it took to reach its maximum height. So delta t is unknown as it's approaching delta d of 0.46 meters up, which we calculated in sample problem number 3. And we can refer to 0.46 meters or its displacement as its maximum height, the maximum height that the ball traveled. So let's try to find an equation that incorporates everything that's given in what we want, delta t. Now there are many choices as we have almost every variable possible here. The equation that I'm going to choose is v2 is equal to v1 plus a delta t. If you want, you can choose a different one. Try it out and see if you get the same answer as me. We rearrange this equation for delta t and we get v2 minus v1 divided by a. Sub and solve, we get 0 minus 3 meters per second up, and I know I'm going to have to switch the bottom acceleration so that it is up as well, so I'll go right ahead and write it as negative 9.8 meters per second squared up. You can anticipate these direction changes and save yourself a step by writing it in right away in the same direction as the other quantities. Punch this into your calculator, report your answer to 2 significant digits. Keep in mind that the time will be positive, and that's a good thing because negative time doesn't exist. If you do so, you will get an elapsed time of 0.31 seconds. So we conclude this question by saying it takes 0.31 seconds for this ball to reach its maximum height. So freefall kinematics is really just an extension of kinematics from section 1.5. We're looking at uniformly accelerated objects that are traveling in a straight line. This time the frame of reference is flipped and we're looking at up and down. And we realize that the acceleration, which is constant throughout freefall, is due to gravity and is given a value of 9.8 meters per second squared down. Try the practice problems and see if you can do well with these examples.